Good morning. Today we will discuss about distortion in welding. So before understanding distortion, it is imperative that you know something about the cause of distortion, which basically is residual stress. So today's lecture we will dedicate to residual stress in understanding what is residual stress, how residual stresses are formed in welded structures, and then certain measures to prevent the accumulation or development of residual stress. So, residual stress is actually self-explanatory. We know the meaning of what is residual and what we know the meaning of what a stress means. So, residual stresses are stresses which are present inside the body of a body of any material, which is actually leftover stresses of certain externally applied loads or certain internally generated loads. So why residual stresses are formed during welding is basically because welding is a non-uniform heating and cooling process. Like in welding, the material is not uniformly heated and uniformly cooled. Welding happens only in a very small area, and that too not in a very uniform manner. Very sudden increase in temperature happens. I have been mentioning this right from our first class that within a fraction of seconds the temperature is taken from room temperature to melting point temperature, and then within some seconds the temperature is brought down from melting point to a very low temperature. So due to this non-uniform heating and cooling, it produces very complex thermal stresses and strains inside the material, and this actually gets accumulated and can form residual stresses. So distortion basically happens when these residual stresses are accumulated, and then the value of this accumulated residual stress is exceeding an yield point or the yield point strength, or the yield strength. Then it causes a distortion, which is a plastic phenomenon, a plastic deformation. Residual stresses has lot of impact in the engineering material. It will reduce the service life, it can cause failure, it can result in brittle failure, and the other things which you may not know is these residual stresses will decrease the corrosion resistance of the material. Corrosion property will be diminished and can cause various corrosion phenomena like stress corrosion cracking, then hydrogen induced cracking. Hydrogen induced cracking is not basically corrosion, but in turn it's a type of failure in weld structure, which I think I have already discussed. Then it reduces the fatigue strength of the material. The residual stresses can either be tensile in nature and or compressive in nature. The most undesirable form is tensile residual stresses. In most of the cases, compressive residual stresses are beneficial, but even in the otherwise, compressive residual stresses can reduce the ability to resist buckling and collapsing of the material. As I have told before, when residual stresses are exceeding the yield strength or yield point of the material, it causes distortion, and this distortion will naturally result in misalignment, difficulty to assemble the individual components, and also will affect the appearance, will cause a very wavy appearance, and then will result in a very poor appearance. Residual stresses are stresses which I have already told, which remain in the structure when all the external loads are removed, and can also be generated due to um, internal stresses produced, which I will be discussing in slight detail in our coming slides. The main causes of residual stresses during welding are, as I have already told, the local heating and cooling, which is very uniform, very non-uniform in nature. Then due to the shrinkage forces developed during the cooling process, so the shrinkage will produce certain residual compressive as well as tensile stresses. This tensile stresses would be formed basically adjacent to the area where it is cooled, and compressive stress slightly away. And microstructural changes during solidification, which I will be discussing in our subsequent slides. the temperature is raised to melting point, as I have already told. And what happens basically is that as we do the welding, we move the heat source from one point to other. And during that, even during otherwise, even without the motion of the heat source, the materials would be having very high thermal conductivity. And due to that also, the sudden cooling will happen due to the thermal conductivity and rapid dissipation of heat. And also the heat affected volume, not the heat affected zone, I mean the area, the volume where the heat is getting actually affected is actually very low, so that the bulk of the material won't be having a high temperature, due to which there will be a there will be a very large temperature gradient, due to which the sudden cooling will happen, which in turn will add up to the thermal stresses produced, because thermal stress is directly proportional to alpha delta T, that is directly proportional to temperature gradient. So the phase changes occur during the temperature increase or during the thermal cycle will actually have have an effect on the stresses produced. The reason is why, because when as we all know, we might have studied about in carbon equilibrium diagram, or I have told in many of my previous classes itself, when a material is taken from one temperature to other temperature, the stable phases which are corresponding to that particular temperature will be formed. Say for example, the ferrite phase, which is stable at room temperature, when the welding happens, the temperature will become 500, 600, 900 until the melting point temperature. So for all these particular range of temperature, there will be a stable phase correspondingly. So say for example, ferrite will be changed to austenite will be changed to another delta ferrite, and then due to the cooling, many other microstructures will be formed like bainite, then again ferrite, and due to the rapid cooling, martensite can form. So all these phase changes will happen. We might have also studied that each of these individual phases will have different atomic packing density, and when the density is different, there will be corresponding change in the volume. Say for example, when ferrite phase transforms to austenite, this austenite will have a higher density. When it has a higher density, it has a lower volume than ferrite. So what happens is that there will be volumetric differences which will cause a thermal which will cause an induced stress formation, because you see, when the atom, just imagine that the person who is sitting adjacent to us is getting enlarged, so naturally we will feel that force nearby. Like say for example, just imagine a couple of balloons packed serially. When we are filling air into one balloon, this the volume increase will naturally cause stress in the other adjacent balloons. So similarly, whenever there is a phase change inside the microstructure, that particular phase change is accompanied by a volumetric change, and that volumetric change will naturally cause an internal stress. So that's what. So the idea is very simple. So as temperature increases, the other thing what happens is that the Young's modulus of the material will decrease, and hence the elastic portion of the stress strain will not be having a straight line. It will be having a non-linear property. Normally, what happens is that for ship construction, as well as for most of the engineering construction, not in heavy engineering, but in most of the other normal engineering construction, the steel plate which is used will be having a thickness of less than 25 mm. So these residual stresses produced in the thickness direction are normally ignored when the thickness is below 25 mm. But when the thickness is very high, say for example 50, 60, 70, 100, we have to consider the residual stresses developed in the thickness direction as well. So the distribution of longitudinal stress can be approximated by an equation called Masabuki and Martin. I have not written the equation here clearly because it's actually not that useful, because we just need to understand that in which direction the residual stresses would be significant. That depends on the thickness, that depends on the stress which is applied, etc. Say for example, in our previous slide itself, we have seen that for thicknesses which is less than 25 mm, this distribution is not that important when we consider the thickness direction. As a thumb rule, you just understand that tensile stresses will be seen at areas dominated by thermal stresses, and compressive stresses will be seen in areas which is dominated by transformation stresses. Transformation basically means the microstructure transformations. Transformation stresses are normally diminishing as the area being transported becomes wider, because you see, let's see that if there is a transformation which is widely transformation which is happening over a large area. When it is happening over a large area, what happens is that the small residual stresses will get cancelled each other, because there will be a corresponding stress developed in the opposite direction as well, due to the transformation of a particular phase in the other side. So when it's happening over a very large area, this transformation stresses will get normally diminished. So let us now understand the factors for setting up residual stresses. There are many reasons. Where you see, I have spoken about welding. In welding, there's a uniform heating, non-uniform heating, non-uniform cooling, etc. But there are many other aspects as well. Being engineers, we need to understand the root cause to solve a particular problem. Wherever we find any problem, we have to understand the root cause of the problem. Only addressing the root cause will eventually lead to solving the issue. So let us understand the basic root causes, the significant root causes. Like it depends on the quality of the material and filler metal. We'll come to that one by one. Then shape and size of the weld. Then the amount of the weld deposited, weight of the weld deposited. Then the type of joint and the method of weld sequence formed. Then the heat input, which we have already discussed. This heat can also be there not because of welding, but also due to the flame heating or gas cutting, which we use for cutting the materials. Then the type and structure of the neighboring joints, because you see, we can almost correlate all these scientific things with our personal examples itself. So you see, whenever we have a neighbor who is a very troubling person, we'll also feel discomfort. Samely, it depends on the neighbors as well. The stresses which we experience, which can be correlated to our internal stresses, the pressure from our parents, friends, etc. So it depends on the type of structure, the neighboring joints, expansion and contraction of the workpiece. That depends on the property of the parent metal, the rate of cooling, and then the stress already present in the weld. Because you see, just understand that if we are already having a lot of personal issues, and then another neighbor is coming and interfering, then it will naturally affect our increase our residual stress. So the 9th point is the stresses already present in the weld. Whenever I have studied this distortion and the residual stress during my college days itself, I used to just understand it in a very social way. Like, it's very easy for us to correlate with our personal things and then better understand scientific concepts. It's not always possible, but I try to adopt it wherever it is. Wherever I find it suitable to compare. So methods of stress relieving are, we can first consider the stresses in our design and then design accordingly. Then material considerations, preheating, welding procedure, welding sequence, post-weld heat treatment, natural aging. I have the spelling is mistake, not raging. I'm extremely sorry, it is aging. And peening, and then vibratory stress relieving. All these things are basically self-explanatory, except the point number 9. But anyway, I will discuss all these points from 1 to 9 slightly in detail in our subsequent slides. So let's start with design considerations. You see, I have already mentioned the root cause. One of the root cause is the weight of the amount of the weld which is deposited. So let us try to reduce it. So we shall design in such a manner that the smallest weld size is actually required for welding the particular thing. That means we need not over design it. We shall design only for the optimum weld size. And then preferably we shall use fillet weld over butt welds. So that means we can we can try to avoid the weld sizes. Like We can try to avoid the welding of the entire equipment itself. Like say for example, if bending is possible, do bending and then provide stiffness with stiffness for additional stiffening. For that we just need to do some fillet weld on the stiffness rather than welding the butt and then increasing the quantity of the weld. Then the third one would be prefer division of structures into smaller assemblies. Like you see, whenever we are constructing, it's better we make small units and then assemble. The thing is that for the weld associated with the welding a smaller things would be not that high compared to welding the entire thing, because in that case the root gap will be more, the thickness will be more. Then we have to do double gouging and then welding, because it will add on to the weld of the entire structure. Then transverse weld joints shall be arranged in a staggered pattern, because transverse in the sense perpendicular to the length. So transverse weld joints shall be preferably in the staggered direction, because you see, whenever there is a longitudinal as well as a transverse area, the transverse area will be having a smaller, what do you call, cross section or the area. So if whenever we are having some weld in the transverse direction, and if these all things are accumulated together, then it is easy for the stress to get added up. But if it is staggered, the advantage is that this addition of stresses won't happen. And the amount of staggering is preferably not less than 20 times the plate thickness. These are all basic thumb rules, but you cannot consider this as a universally accepted thing, but these are all thumb rules which you can adopt in our practice. Then cutting a mouse hole is it's self-explanatory. Just imagine a small hole through which a mouse can pass, but it's technically not a mouse hole, but we just call it as a mouse hole. Cutting a mouse hole in a theoretical manner where the longitudinal as well as transverse welds are overlapping, so that whenever we are providing a mouse hole, then there won't be double welding over that. That's the idea is very simple. So this avoids overheating at the intersection, and also you see the care which we have to provide is that all these rounded whenever we are cutting off a area, we have to ensure that there is no sharpness, because this sharpness will in turn cause stress corrosion and then will eventually lead to fatigue failure. Can lead to fatigue failure, but not in all cases, but definitely the fatigue age will get reduced as per the SN curve. So material consideration. So the materials preferably shall be only selected so that these are weldable materials. Then the properties like melting point, specific heat, thermal diffusivity, thermal conductivity, coefficient of thermal expansion, modulus of elasticity, then the ductility at high temperature, the yield strength, everything will influence these residual stress form. You see, whenever there is a high melting point, the temperature has to be taken to that particular temperature, melting point temperature. So that delta T will get increased. Delta T increase will result in thermal stress. Thermal stress will result in residual stress. So all these things are interrelated. Say for example, specific heat. If the material has a very high specific heat, naturally the residual stress will increase. If the thermal diffusivity is very high, that means the dissipation will be very high. Dissipation is very high means it leads to very rapid cooling. Rapid cooling means delta T is very high, so it again increases the residual stress. Coefficient of thermal expansion is basically the same. Then the modulus of elasticity I have already mentioned. Then higher yield strength. Higher yield strength means is proportional to, I think it is squared. I don't recollect the correlation between elastic, but it's slightly, just Google it and find out. The elastic energy is directly related to yield strength. When the yield strength is getting increased, elastic energy is getting increased, and it promotes brittle fracture. Preheating. I think you might already know what preheating is. Preheating is basically done to reduce the temperature gradient. Temperature gradient, when it is reduced, what happens is that thermal stress is getting reduced. So preheating can be done by many methods. Like we can the normal practice is we will just heat the heat the material with a propane gas or an acetylene gas. Acetylene gas is technically not used, but technically we shall use only propane gas because it is less oxidizing in nature. And then this preheating will take the temperature of the particular material prior welding to a slightly higher temperature. That means higher than the room temperature, so that delta T means the temperature before welding to the temperature, the maximum temperature during welding. That means normally the melting point temperature, that delta T is getting reduced, so that thermal stress is getting reduced. So it reduces the heat input by welding, then reduces the width of the fusion zone as well during preheating. Then preheating is actually very important for materials with high thermal diffusivity. That is because we have to ensure that the welding is happening at a particular temperature itself. And this particular when the thermal diffusivity is high, it is very difficult to maintain the initial temperature because it will be easily dissipated to the surroundings. It is also good for material with low ductility at high temperature. Say for example, custom is the classic example to that. Then preheating shall possibly be not localized because that in turn will result in a residual stress. It is preferably like 80 to 70 mm on both sides of the well, but that is the minimum thing which you should do. Then reduces the cooling rate in HIZ, and then improves the microstructure as well, and reduces diffusion of hydrogen, because you see diffusion of hydrogen is that when it is taken to a high temperature, then it is actually sufficient amount of time is got for the hydrogen to escape out, and then then the residual hydrogen which is there in the microstructure can be reduced, which ultimately reduces the diffusion of hydrogen. And then cold cracking is also known as hydrogen induced cracking. And it also ensures that the hardness level is below 350, because whenever the temperature is taken to a preheat temperature and then welded, and then the welding is over, what happens is that due to the temperature already present, there won't be any rapid cooling happening, because there is already a temperature there, because all known the preheating as well as interburst temperature. So what happens is that desirable microstructures are formed, and due to which the hardness value is not that very high. The other requirement of hardness value is not with regards to residual stress, but also with regard to NACE requirements. NACE requirements is with regards to corrosion. So say for example, when you operate in offshore conditions itself, there are particular limitations to the corrosion. That is actually an acceptance criteria as per NACE standards. Preheating also depends on the carbon equivalent, the thickness of the material as well as the thickness of the weld. So there are many what you call the tabular columns in sections like ASME section 8, AWS section D 1.1. And other standards as well, where we see the nature of the material. There are P numbers which I think I have mentioned already. P numbers are there. Based on the P numbers, thickness values will be there. Based on the thickness value, we have to see the desirable preheating temperatures for that particular pre-qualified preheating temperature for that particular material, for that particular thickness as well. Then whenever we are doing welding, we have to select the process which will result in minimum residual stress. For example, backstep welding and skip welding. From a production point of view, backstep welding and skip welding will take a lot of time, because it's a very time consuming process. But wherever you need a particular distortion to be minimized, or particular residual stress to be minimized, it is imperative that you go with some you have some time to bank on. Otherwise these things will keep on repeating, like distortion, residual stress. But it's not practically possible for us to do backstep welding in all the process, because you end up maybe 100 years in welding the entire ship, because it is as time consuming as that. So backstep welding I will slightly explain. It's a very simple thing, backstep method, because wherever you go in industry, the welding person, the concerned with will boast in such a manner that the only person who know backstep welding is that particular guy. It's a very simple thing. Just understand that it's backstep. It's a very self-explanatory thing. The basic principle is that the successive welding is done or finishes where the weld just don't complex it. Just understand that. Just see the figure. Number one starts from right to left. Number 2 will start from right to left in such a manner that number 2 will end where number 1 has started. It is as simple as that. Okay, and number 3 will end at the point where number 2 starts. Just see the figure and understand. That's all backstep welding is. And just keep in mind that the weld length shall not be exceeding 2.5 times the thickness, as well as the spacing provided is not 25 times the thickness. But that is actually not strictly followed, but the backstepping principle is what we normally follow. But it is important that these things are also followed. And complete part cooling in between weld run shall be ensured, because otherwise that weld which is produced there, the residual stress which is produced there will get added to the other thing, because ensure that complete part cooling between weld runs are there. Skip welding is basically the same thing, the similar thing. It's also self-explanatory. A short weld length is deposited one part, and the next weld length is done at some other distance, so that the basic thing is accumulation of stresses won't happen. Welding sequence is a very simple thing. Just consider a small square. When we are doing welding in one location, corresponding residual stresses will be formed, and that residual stresses will try to exert its influence in nearby areas. Design the sequence in such a manner that the stress produced in the second location will counter the stress produced in the next location, so that it tries to nullify each other. This welding sequence considerably reduces the development of residual stress because of the opposite actions, basically, because the stress produced in one location shall be cancelled out by the stress produced in the other location. And normally what we do is a transverse welds are normally staggered. This we have already mentioned. And the staggered transverse welds are welded first, and then we proceed with the longitudinal welds. So this is a normal thing which we follow whenever we do have a longitudinal as well as transverse welds. Firstly, we have to tackle the transverse weld, and then you proceed with the longitudinal welds. Then post-weld heat treatment is the ulta of preheating, and not the ulta, but it is very similar, because whenever we read a book, we read about preheating and post-heating, because the idea is very simple, just to control the rate of cooling, the rate of heating, etc. It is basically done for stress relieving, but it is also done to control the rate of cooling, which will determine the microstructure produced. And it also depends on the material composition. We can get reference from section 9, ASME section 8, then AWSD 1.1, etc. It can be applied locally or all the entire structure. You see, I will show one picture in the next slide where the post-weld heat treatment is done locally. But if the structure is very small, we can put the entire structure in a controlled furnace and then control the temperature. Here the care shall be taken in controlling the rate of heating, the rate of cooling, the temperature to which the post-weld heat treatment shall be done, and the holding time. Because especially for microstructure control as well as for stress relieving, this particular temperature to which post-weld heat treatment is done shall be maintained for maybe 5 hours, 3 hours, 2 hours, 1 hour, etc., depending on the thickness as well as on the material property. Usually when the temperature is taken to 540 or 815 degrees Celsius, the hardness will slightly get reduced. And this is a slide showing you the post-weld heat treatment done with asbestos. Basically what happens is that the area where the welding is to be done will be heated up with a electric coil, and then heat is applied. In order to prevent the dissipation of heat, asbestos sheet will be wrapped around it, and then temperature thermocols will be applied, so as to understand what would be the temperature drop, what is the present temperature, what is the rate of cooling, etc. Natural aging is self-explanatory in the sense, if you consider yourself, like we will just understand that we are having a lot of internal issues. Naturally it will get reduced, we will get accustomed to it. It's not that easy for engineering material, but because as time proceeds, certain realigning of the crystal structures will be formed, and then which can but it's a very time consuming thing. Even for us it is a very time consuming thing without any external help. we can get rid of our issues, but it takes a considerable time. Say for example, 80 to 90% of the stress in an engineering material will be reduced over an year only. It's not a very acceptable thing, but in certain cases, certain materials, the natural aging will be slightly more than the other, but even in that case, it's like, and the time duration is very high, not acceptable. Peening in the sense, light hammering the weld. Peening is just a small hammering with a ball tip chipping tool. Light hammering of the weld with the surrounding material is done with a moderate force. Then the temperature at which it is done is basically either 450 degrees Celsius or above, or below 550 degrees Celsius. Otherwise, what happens is that it can cause cracks. And also the other disadvantage of peening is that if some microstructure cracks are there, this peening will just close the crack temporarily, because it is actually imparting small compressive stresses. The basic thing I have already told is that the residual tensile stress is what causes the problem. So here the residual tensile stress is slightly nullified with certain compressive loads which are given. And the other disadvantage is that it can also affect the ductility of the material. And peening is also not advised on the first layer. The first weld layer, please do not do peening, because there is a root joint, and and that won't be a very thicker weld bead. It can easily displace the weld because the weld is not that strong, and also it can even cause crack on the weld. Peening in the sense, you can see if you are very much if you're having a lot of personal issues, if somebody comes and give you a pat at the shoulder, we can see that we get some relief. But if somebody, you see, if the temperature is very high, or if it is below a certain degree, then it is not that good for peening. Similarly, if the patting is very is not okay, let's leave it. Vibratory stress relief. I have given a link here. Just see what that is. It's a very interesting video. Vibratory stress relief is a very interesting type of stress relieving. Here what happens is that we induce vibration on the material, and will be giving what you call a low frequency high amplitude vibrations, and we'll try to match the vibration frequency with the resonant frequency of the material. So during that, what happens is that the material will vibrate in the resonant frequency. So the advantage of this particular thing is that it's a very effective stress relieving process, and there is no thermal effect. So there won't be any microstructure issues, there won't be any mechanical property changes, as well as no distortion due to lack of heat. Okay, because in all the other cases, majority of the cases, except for even for peening, it's associated with certain temperature. So that temperature addition which is given to rectify the residual stress or distortion can in turn can increase the residual stress as well. But in vibratory stress relief technique, we are not depending on any thermal means. Only we are trying to give a vibration with a small motor, and then trying to match the frequency with that of the resonant frequency. Up to 80% of the residual stress can be relieved using a vibratory stress relief technique. And the beneficial effects can also be found in the distorted crystal lattice. Okay, so just go through the let's see whether that can be played.